Now let's take a look at the self-learning process used in MoCo. So by comparing it with DINOv, we can have a better understanding of their similarity and their difference. The full name of MoCo is momentum contrast. So here is a self-training scheme of MoCo. We see that this image is very similar to the image we see previously for DINOv. So there is a student network which is called a query network, passed through a query encoder, and there is a teacher's network. The difference is there a list of the keys. Then we pass these keys into the momentum encoder. Then we generate multiple encoded keys. This is encoded queries. Then we calculate the contrastive loss. We compare the similarity between the query and each of the keys. Then calculate the contrastive loss. We also apply the no gradient operator to the key branch or teacher's branch. So the loss only backpropagate through the student's branch and get student's network parameter updated. And then similarly, the teacher's network, the key branch network, was updated similarly using a exponential moving average. So normally in this scheme, so for the network need to keep a very large set of keys. If we look at the contrastive loss used in MoCo, so it's InfoNCE, information noise contrastive estimation. So in order to calculate this InfoNCE loss, we need a encoded query and k+1 encoded samples. So as we mentioned, this key is normally very large. We have a very large of samples kept in the key, and there among them there is a single positive key. This positive key is exactly the one that matches query, because basically this query and positive key are different copies of the first different copies of the same image. Then the contrastive loss basically act as a k+1 bit classifier that tries to classify query as the positive key with similarity measured by dot product. So the similarity is calculated by the dot product between the query and the key. Then by calculate this loss function, basically this loss function means if we minimize this loss function during training, then we actually train the model to assign high similarity to the between the query and the positive key, but assign low similarity between the query and the negative key, all of the negative keys. So that means positive samples are put together and the negative samples are pushed apart in this embedding space, because these are all encoded query and the key. So what this means? So why we have a list of samples? Because we have two versions of the same image. For example, for the same image, we have one version like this, um, this is maybe this is a query, and we have another version like this. This is a key. Because this key, these are come from the these are two versions of the same image, so this key is a positive key respects to this query. Besides, we know that these are should be same. We want to pull this. We want to pull these two together. We also need to have a large number of negative keys that we know this is a cat, and we also have to let the network realize that this is a cat, but this is not a dog, this is not a apple, this is not a tree, this is not anything else. So that's the reason we normally need to keep a large amount of negative keys. We need to push negative samples apart in the embedding space. Now let's take a look at the pseudocode of MoCo. So for MoCo, we have query network and a key network. Both network has the same structure, which use ResNet as backbone. ResNet project input image into a 128 dimensional vector. So for Q, we keep all of the negative keys in a queue. So here we keep, as we mentioned previously, we will use a large number of the keys, which is 65536. We keep all of these keys in the queue. So the dimension of this queue is 128 by 65536. Initially, we random initialize the key network and the query network. Then during training, each time we load a mini batch of samples. So here we choose a small number of samples, like 3 as a mini batch. So advantage of doing this small mini batch is it decouples the dictionary size k from the mini batch size n. Here, because we maintain a large k, so we can use a small n, and so that will decrease the requirement for memory usage during training. Then after we load a data sample, we apply two versions of random augmentation to the same input. Then we get query and the key. We get two versions of the same input data. We feed these two versions through the query network and the key network respectively, then get the encoded query and the encoded key. So because we use ResNet as the encoder, so giving the input query and the key, which are represented as a 3-channel and 224 by 224 color image. There are 3 samples in this mini batch. It will be mapped to 3 128 dimension feature vector, use a ResNet encoder. Then we apply a stop gradient operator on the key branch. Then we calculate the positive logit, which is a dot product between the query and the positive key. So the query, the encoded query is 3 128 dimension feature, and the key has a similar dimension. Then we take a transpose of the key, then do a matrix multiplication. We get the positive logits, which are 3 numbers, indicate the similarity measured by product between the query and the positive key. Similarly, we can calculate negative logits, which is a matrix multiplication between the query and all of the negative keys in the queue. So query is the same 128-dimensional vector. Then the queue, we keep a large number of positive keys, negative keys in this queue. So by multiply these two matrices together, we get negative logits. Then we concatenate positive logits with negative logits along dimension 1. After so that means we concatenate this matrix with this matrix, so we get this matrix. What's inside this matrix is plotted here. So the first column are all the dot product between the query and the respective positive key, and the rest of the matrix is the 3 query dot product of the 3 query with respect to all of the negative keys in the queue. So if we look at the index, so this column has an index of 0, this is 1, 2, 3. So this is the logit we get from the output of the encoder. So for this kind of the prediction, the ground truths are 3 zeros because all of the positive keys are from the first column. For all of these rows, the positive keys are from the first column. So the ground truth labels are 3 zeros. Then we calculate the regular cross entropy loss between the predicted logit and the ground truth label. I use this equation. So basically, as we mentioned, by minimize this loss function, we are actually train the network to pull all of the positive keys and the query together and push negative keys and the query apart. So then after we calculate the loss, we use stochastic gradient descent to do the back propagation, then update only the query network. And the key network was updated using exponential moving average. This is also the momentum update. Then finally, after the update, we add the mini batch we obtained in this loop, which is a 3 encoded 128-dimensional vector. Appended this vector at the end of the queue. So this is actually the samples encoded by the previous key encoder. Then we remove the front 3 keys from the queue so that we keep the dimension of the queue to be constant. So this is a pseudocode of MoCo. This is the self-super learning training method that MoCo takes.